Okay, let's see if we can review a little bit from pre-calculus and how to rewrite. If you notice, all these are fractions, and rewrite them using negative exponents. Well, this is the same as 1 divided by x, which we can write as fraction that we're more used to as 1 over x, which is equivalent to x to the negative 1. The negative exponent means a division problem. So in this case, we're taking a division problem and writing it as a negative exponents. So once again, this one is 3 over x to the fourth, and that is equivalent to 3 times x to the negative 4. Because we're dividing by x to the fourth, we can rewrite that as x to the negative fourth. Here's one that's 5 over x to the 2/3. So following the same pattern, we should be able to see that that is 5x to the negative 2/3 power. Be careful with this one, because this is 9 to the negative 1/3. Notice there's no x. So we cannot rewrite this in the form ax to the b because there's actually not an x there. So this is the one that you would just have to leave as is, and you can't simplify and write it in that form as there is no x. Okay, here's some problems that kind of go the other way. If you notice, these are the equations that are written with negative exponents, and we're asked to rewrite it without a negative exponent. So keeping in mind that a negative exponent means a division problem, we can go the other way and rewrite this as a division problem and say this is 3 divided by x to the 1/2 power. Which, remember, 1/2 power is like a square root, so if we wanted to simplify this even further, we could say 3 over the square root of x. 5x to the negative 4 then becomes 5 divided by x to the fourth without a negative exponent. Now notice this one is 7 divided by x to the negative 1/2. So if I want to change this to a non-negative exponent, I got to actually change this to 7 times x to the positive 2 power. So this is one that has a negative exponent and division problem, so they kind of cancel each other and make a multiplication problem. And again, this is another problem that there's no x, so you can't simplify this. So this is as simplified as you can make this. Okay, next set of problems involves how to get rid of parentheses. If you notice, we have a plus 3 squared, then we have a plus b cubed, and then a plus h to the fourth. So these require a series of generic rectangles, which I will do here on the next slide. Okay, let's look at the first problem. A plus b 3 squared, but I'm going to think of it as a plus b squared, and later on substitute b equals 3. We'll set some things up for later on. So a plus b squared, remember, equals a plus b times a plus b. So I'm going to use a generic rectangle to help me figure out what that is without parentheses. So a plus b, a plus b. So I figure out the inside of the square. So a times a is a squared, a times b is ab, b times a is also ab, and b times b is b squared. And I look for like terms, and I notice, hey, these two are like terms. So this is equivalent to a squared plus 2ab plus b squared. Remember, b was 3, so if I substitute that into my equation, I realize, oh, that's a squared plus 2 times a times 3 is 6b plus 3 squared, which is 9. And so this is an equivalent equation written without parentheses. Now let's take a look at a plus b cubed. Okay? So remember, that means a plus b times a plus b times a plus b. Well, we just found out from the previous problem that a plus b times a plus b is a squared plus 2ab plus b squared. So I'm going to take that answer and multiply it by another a plus b, which again requires a generic rectangle. A little bit more complicated than the previous problem, but still can be done. So a plus b, and then across the bottom a squared plus 2ab plus b squared. So again, I find out each individual box. A times a squared is a cubed. A times 2ab is 2a squared b. A times b squared is just that, ab squared. B times a squared is actually a squared b. b times 2ab is 2ab squared, and b times b squared would be b cubed. Again, I look for like terms, and notice, just like the last problem, they show up diagonal one another, which is helpful. It helps me make sure I got everything right. So this becomes a cubed plus 3a squared b plus 3ab squared plus b cubed. So this problem expanded without parentheses becomes this. Now, the last one is a plus h to the fourth. Okay, so getting more complicated. But again, the idea is that this is a plus h times a plus h times a plus h times another a plus h. Well, again, using the results from the previous problem, I know that the first three has got to come out a cubed plus 3a squared h plus 3ah squared plus h cubed, and then I'm going to multiply that whole thing by another a plus h. So again, generic rectangle works best here for me. But again, a little bit more complicated than before. So a plus h here, and across the bottom a cubed plus 3a squared b plus 3ah squared, and then h cubed. And again, I fill out all the individual parts. So this is a to the fourth, 3a cubed b, 3a squared b squared, and ah cubed. And down here I have an a cubed h, 3a squared h squared, should be an h here, plus times 3ah cubed, and h times h cubed is h to the fourth. And again, just like before, all the like terms are diagonal from one another. Okay? So this becomes a to the fourth plus 4a cubed h, oh my b's became h's, sorry, plus 4a squared h squared, I'm sorry, plus 6a squared h squared, plus 4a h cubed, there should be cubed here, plus h to the fourth. And so this is how you expand that problem without parentheses. Kind of a long process, but you get the idea. Okay, what we have here are two definitions of a derivative that, while you don't have to ever memorize and be able to tell me these formulas, you do have to recognize that these are derivatives. And just as a helpful hint, if you know this part of the equation sort of looks like a slope formula. y2 minus y1 over the change in x, which is sometimes written as x2 minus x1. So both of these formulas have something that looks somewhat like a slope formula. Not exactly, but it's very similar. But the big difference is that there's a limit notation in front of both of these, and this is what makes it into instant slope, and therefore a derivative. Okay? So what we're going to do is use this formula. I'm going to use this form of the formula to actually see if we can find the algebraic derivative for x cubed. Okay? Okay, so we're going to use this definition of the derivative to see if we can find the algebraic derivative of the equation f of x equals x cubed. So this says to go ahead and find the limit as h goes to 0 of f of x plus h. Well, what that means is sort of take x plus h and substitute in that equation. So this says that whatever I'm substituting, in this case x plus h, go ahead and cube it. And then go ahead and substitute x into that equation. So when I substitute x in that, I just get the equation again, x cubed all over h. So using what I learned from the previous slide, I realize this is the limit as h goes to 0 of, if I expand x plus h cubed, I get x cubed plus 3x squared h plus 3xh squared plus h cubed minus that x cubed all over h. So this is equivalent to this. It's just expanded out using the generic rectangles like I showed on the previous page. Okay, so I look here and say, well, if h is 0, Well, first of all, x cubed minus x cubed is gone. If I notice here, these all have an h in them, and I'm going to divide by h. So I'm really taking the limit as h goes to 0 of 3x squared h divided by h, so the h's cancel. 3x, now I'm going to take this term, 3x h squared divided by h, and I'm going to get 3x, but not only one h, and then x cubed divided by h, I'm going to get h squared, sorry, h cubed divided by h comes out h squared. And so now if you notice here, I've gotten rid of my fraction because I divided all these terms by 1h. And so now I'm left with this problem. I can just simply substitute h for 0. If you notice, these terms both become 0. And so my exact derivative is 3x squared. So here's my original function. Here's my derivative, which we denote with the terminology f prime of x, which is a little apostrophe. We would say it's equal to 3x squared.